Have you ever actually stopped to consider how a simple, totally painless beam of light can reveal your absolute deepest medical secrets? I mean, it sounds straight out of science fiction, right? But every single day, millions of critical medical diagnoses are made, not by a person squinting at cells under a microscope, but simply by shining targeted light through a tiny sample of your blood. It's this incredibly powerful diagnostic tool that literally forms the bedrock of modern medicine.
Welcome to This Explainer. Today, we're taking a deep, comprehensive journey into the completely fascinating world of clinical biochemistry, and we'll be guided by the highly detailed experiments presented by Dr. Chem. We're going to explore the actual laboratory methods that transform light into life-saving data. So if you've ever had blood drawn and thought, how on earth do they extract so much information from those tiny little vials? Well, you are going to love the journey we've mapped out for you today.
Okay, let's dive right into this. Here is our agenda. We'll start with the complex blood matrix, followed by the magic of light, and then diagnosing by color. After that, we'll cover advancing to whole blood, and we'll wrap the whole thing up with point-of-care diagnostics.
Section 1. The complex blood matrix, navigating a microscopic soup.
So to understand this, we first have to realize that whole blood is an incredibly crowded, opaque suspension. It's essentially this dense, microscopic soup. You've got about 45% erythrocytes, those are your red blood cells. Then there's 54% plasma, which is the liquid part holding all the proteins, glucose, and lipids. And finally, making up just a tiny 1% sliver are the leukocytes, or white blood cells, and your platelets. When you think about it, the diagnostic challenge here is just immense.
So the big question really becomes, how do we isolate a single invisible molecule, something like glucose or bilirubin, in this incredibly messy, crowded soup? Well, the brilliant solution is spectroscopy. Think of spectroscopy as a highly specialized mathematical light filter. It has this amazing, unique ability to completely ignore all the cellular noise and see only the exact molecular signatures we're searching for.
Which brings us to Section 2, the magic of light, filtering the noise.
Now, the crucial point here, the real secret to how this works, is the Beer-Lambert law. This is the absolute bedrock of clinical biochemistry. Basically, when we shine a specific intensity of light through a colored solution, the amount of light that actually makes it through is reduced by absorption. The Beer-Lambert law gives us the mathematical formula proving that the absorbance of that light is directly proportional to the concentration of the chemical we're looking for. To put that into plain English, the darker the specific color in our prepared sample, the higher the concentration of the disease marker. It's an elegant law that directly connects a simple color change to the severity of a medical condition.
And we see this applied constantly. For example, this ratio calculation is the exact math used in modern pulse oximetry. By pulsing two highly specific wavelengths of light, red light at 660 nanometers and near-infrared light at 940 nanometers straight through your finger, a sensor measures the absorbance of oxygenated versus deoxygenated hemoglobin. That ratio dynamically calculates your critical oxygen levels in real time, and it is all based on how much light makes it through to the other side.
Let's move to Section 3, diagnosing by color, clinical biochemistry in action.
And this brilliantly illustrates how targeting specific colors yields data that literally saves lives every single day. For instance, right at 540 nanometers, we check for anemia by quantifying hemoglobin. Shift just slightly over to 546 nanometers, and now we're looking at total bilirubin to diagnose jaundice or liver disease. Down at 505 nanometers, we're measuring blood glucose for diabetes management. It creates this beautifully precise optical map of your health.
Now, to actually utilize those light wavelengths, Dr. Chem's presentation outlines the incredibly specific experiments lab technicians perform to prepare the blood. It's fascinating. For hemoglobin, Dr. Chem details Drabkin's method, where a reagent is added to create cyanmethyl-hemoglobin, which peaks perfectly under 540 nanometer light. For bilirubin, he highlights the Evelyn-Malloy method's Dialzo reaction, which generates a pink-purple product that's readable exactly at 546 nanometers. And for glucose, he explains the GOD-POD enzymatic method, which creates a highly specific quinona imine dye. We are basically chemically engineering the blood so it reveals its secrets to the light. It's amazing.
And of course, the ultimate goal of all these light-based diagnostic measurements is accuracy. We want to pinpoint specific normal reference ranges with 95 to 100% accuracy, just like finding optimal oxygen saturation. Hitting those precise numbers tells a doctor instantly whether a patient is stable or in critical distress.
Section 4, advancing to whole blood, the Raman revolution. So traditional laboratory methods, like the ones we just talked about, require centrifuging to separate the plasma from those red blood cells, plus adding chemical reagents. But here, Dr. Chem highlights a massive absolute paradigm shift. Enter Raman spectroscopy. This allows us to shoot a near-infrared laser directly into unprocessed whole blood and simultaneously measure multiple analytes like glucose, urea, and total protein instantly. No spinning in a centrifuge, no sample processing, and zero added chemicals.
Now, what's really interesting is the unbelievable complexity of the optical system that makes this possible. Because whole blood heavily scatters and absorbs light, capturing a usable Raman signal is frankly incredibly tough. Researchers at MIT had to design this highly specialized, non-imaging optical setup. There's this crucial piece of hardware called a paraboloidal mirror. It's precisely positioned over the whole blood sample to collect the incredibly weak, multidirectional Raman light that scatters off the target molecules. Essentially, it filters out the blinding background noise so the spectrograph can actually read the data.
And to even build a machine like that, those MIT researchers had to run these brilliant Monte Carlo simulations. They broke the physics down into 3 distinct steps. First, photon propagation, basically modeling how an incoming photon navigates through a turbid, murky medium like blood. Second, they calculated the probability of a Raman launch, which is the exact moment a target molecule scatters that light into a new direction. And third, Raman propagation, tracking how that newly emitted Raman photon navigates back out of the dense blood to hit the detector. They were essentially tracking a single tiny particle of light through a microscopic maze.
Let's move to Section 5. Point-of-care diagnostics, the future is miniature.
As you'll see, the massive desktop machines that used to take up entire laboratory benches are being aggressively miniaturized. Take devices like the Ocean ST spectrometer, for instance. This is tiny photonics technology that literally fits in the palm of your hand, yet it's fully capable of complex whole blood absorbance testing and colorimetry.
These tiny spectrometers represent a monumental leap forward for accessible medicine. By merging biofluidics with fiber optics, they can detect whole blood absorbance, identifying serious issues like elevated methemoglobin right at the patient's bedside. This is what we call point-of-care testing. You get answers rapidly without waiting days for a central lab. And as this technology scales up, it's paving the way for applications as critical as early cancer screening and rapid viral detection, all from a highly advanced device about the size of an ice cube.
So, I want to leave you with this provocative thought. As this technology rapidly miniaturizes, what if complex, time-consuming blood labs are eventually replaced entirely by a simple, painless flash of light generated right from your smartphone? We are accelerating toward a future where life-saving, instantaneous diagnostics are universally accessible to everyone, anywhere in the world. And it is all thanks to the incredibly precise science of spectroscopy detailed in Dr. Chem's research. Thank you so much for joining me on this explainer. Keep learning and keep looking at the light.